All right, so today's lecture regards Lecture 4, Part 4, corresponding roughly to Chapter 4, Section 4 of your text. We're going to be talking about L'Hopital's rule and indeterminate forms of functions. So L'Hopital's rule is a technique used for evaluating peculiar types of limits that we haven't seen yet in its entirety. So let's get started. So what we have, suppose we're trying to analyze the behavior of this function, f of x equals the natural log of x divided by x minus 1. And of course, if you're to use, this function is not defined at x equals 1, and we would like to know essentially what the limit as x approaches 1 is for this function. And so what happens is, so we want this limit right here, calculate this limit, and to date we don't really have the only technique we have for evaluating this limit is to create a table, a tabular form, kind of like we did in the early parts of Chapter 2, or you can try and sketch the graph and investigate the limit as x approaches 1 from either side of 1. Okay, so can't apply the limit laws because the limit of the denominator is 0. But if we were to use direct substitution, in other words, plug 1 into the numerator and denominator, we would get this 0 over 0 result, which of course is not defined. But we do classify functions of this type, where both the numerator and the denominator approach 0 as x approaches a, as in this case annotated here. Then this limit may or may not exist, and it's called an indeterminate form of type 0, 0. So when after direct substitution, numerator and denominator go to 0, it's called an indeterminate form type 0, 0 over 0. And we've done a couple of these limits so far from Chapter 2, and so we'll research some techniques for dealing with these types of functions. Okay, so for instance, consider this function, this rational function. Of course, we can obtain the limit by factoring numerator and denominator and seeing that these two factors will cancel. And what else? I'm making sure that this is being recorded properly. Okay. Yeah, so that we make sure that these two factors are canceled, and then once we achieve the cancellation, then we proceed with direct substitution, and you can see that the limit for this particular function as x approaches 1 is 1/2. All right, so what next? All right, now we've already demonstrated a geometric or trigonometric argument using the squeeze theorem for this limit, and of course you can also verify this limit by using a tabular approach. Okay. So we introduce a method known as L'Hopital's rule for actually computing these types of limits in a more efficient manner. So we have what are called indeterminate forms. So clearly, here's another limit problem. The limit as x approaches infinity of the natural log of x divided by x minus 1. Clearly, if we were to use direct substitution, we would have something akin to infinity over infinity, which is yet another indeterminate form type. Okay, so that if you were to kind of abstract out a direct substitution mode for this function, although mathematically you're not allowed to do that. Okay, that's what it would abstractly appear to be like. So, and obviously you can't build a function table for this. Okay, so what do we do? Where do we go? We go to the next slide. Okay. All right, so what's up with the next slide? Okay. So in this, the author talks about there's a struggle between the two. If the numerator wins, the limit will be infinity. If the denominator wins, in other words, for this function, what they're saying here is, here's your function, okay? And as x grows very, very large, it could be the case that the natural log x outpaces x minus 1 in its growth. And if that's the case, then the limit could happen upon infinity. But if the x minus 1 takes on larger and larger values, then natural log of x as x grows large, then it could be the case that the denominator outpaces the numerator as x grows larger, and then in which case the limit could be 0. So which is it? Which is it? Obviously, we can't use a graph or a table for the solution to this problem, so we need a better way of dealing with this. So it turns out that if we have a limit like this, x approaching some number, and both the numerator and denominator approach plus or minus infinity, then we have an indeterminate type of infinity over infinity, and this limit may or may not exist. Okay? All right. So I think you understand the format for indeterminate forms. Okay, so let's see here. So consider this limit right here. The limit as x approaches infinity of this rational function. Well, if you divide upstairs and downstairs by x squared, then you can transform the function into an equivalent function that looks like this. Using the limit laws, then, we know that the limit as x approaches infinity for this term, as well as for this term, will go to 0. So these two terms will die out, and you're left with a half. All right. So you have an algebraic resolution to this limit, but of course, in the preceding problem, you didn't. Yeah, that's it. Okay. So so now we have what's called L'Hopital's rule. Suppose f and g are differentiable, and the derivative of g doesn't equal to 0 on, say, some open interval I that contains a except possibly at a. And suppose that the limit as x approaches a of f of x is 0, and the limit of x approaches a of g of x is 0, or they could this such limit could be plus or minus infinity for f, and then such limit could be plus or minus infinity for g of x. Then, and of course, what's not apparent here is that we're talking about the limit as x approaches a of the rational function, f of x over g of x, okay? Or as x approaches plus or minus infinity. All right, so these are indeterminate forms. Okay, and L'Hopital's rule gives a technique for evaluating limits of indeterminate forms. All right, so L'Hopital's rule says that this limit can be recast as the limit as x approaches a of the derivative of the top divided by the derivative of the bottom, if the limit exists. Okay, so if the limit on the right exists. All right, a couple of caveats. L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. Okay, so you have to verify the conditions, that the functions are differentiable. Also, the limit operation need not be constrained to x approaching a. It applies to right limits, left limits, and infinite limits. Okay. All right. So it's extensible to those types of limits. Okay, so let's see here. What else? Okay, and so here's kind of a rough sketch of how L'Hopital's rule, although this is not a formal proof. Consider this: the limit as x approaches a of the derivative of f divided by the derivative of g. And so if these two functions, if the derivatives of these two functions exist at x equals a, of course we can use direct substitution provided that g prime of a is not 0. And then what we do here is we replace the derivative of a with its definition, the limit delta y over delta x, okay? So, and likewise we replace the derivative of g with its definition, delta y over delta, the limit as x approaches a of delta y over delta x, okay? All right, and so upon further simplifying, what's going on here? So this is the same thing, isn't it? Oh, okay, so we basically do the limit. You see how the limits are in the numerator and the denominator? Well, we can back these two limits out and coalesce the two limits into one limit like so. All right, a little bit of a reverse limit law in action. And then, of course, the 1 over x minus a's will cancel. So that factor cancels, and we're left with this. And of course, Okay, and so we have f of x minus f of a. Okay, uh, this becomes the limit as x approaches a of f of x minus f of a divided by the limit as divided by g of x minus g of a. So how did they get from this step to this step? It's kind of interesting. How do we know this? Well, I'm not sure if this is totally correct then. Let's see here. A little bit as x approaches a g of x. What was that? Why is this true? Okay, so how do we know? This looks to be an error here. How do we go from this step to this step right here? I'm not seeing that offhand. Let's see, maybe there's an explanation in the next slide. Yeah, so they say it's more difficult to prove the version. I think this may be a mistake in the slides. Because this certainly is not true, this statement. Oh, okay. I think maybe this is the assertion they're making. The special case with f of a equal to g of a. Okay. All right. So yeah. So that's how they get away with it. All right. So I should have read it a little more carefully. They're making the assumption that for this proof, that's equal to 0, and they're making the assumption that this is 0. Okay. So that's why. That's where they're able to get away with it. So it won't work, of course, if f of a is not 0, and g of a is not 0. So you'll need something else. Okay, so this is just a specific proof of the 0 over 0 indeterminate form. The other forms will require more research, more work, which we're not, I think according to this note, we're not going to deal with. Okay. All right, so much for that. Okay, so now, but we will just make use of the theoretic result. So now, knowing L'Hopital's rule, we can calculate this limit. Okay, so here's the solution right here. Okay, so solve this problem. Okay, L'Hopital's rule asserts that we take the derivative of the top and the derivative of the bottom, and then evaluate the limit as x approaches 1. And so you know the derivative of the natural log function is 1 over x, and the derivative of x minus 1 is 1. And now that lends itself to direct substitution. So the limit is 1. Okay, so the answer to this question is 1. All right, interesting. Okay, so what's next? Next slide. All right, so let's calculate this limit, the limit as x approaches infinity of e to the x over x squared. Well, clearly, this is an indeterminate form. When you use direct substitution, it'll be infinity over infinity. So L'Hopital's rule, take the derivative upstairs and downstairs with respect to x. You're left with this, okay, and then you still have an infinity over infinity case. So what you'll do is you'll keep applying L'Hopital's rule until you no longer have an indeterminate form. So we need to take this limit problem and carry it over to the next slide. All right, and so when we do that, it'll look like this. So here it is. Oops. Here it is. Okay, so we apply L'Hopital's rule again, and L'Hopital's rule is essentially a recursive operation. You keep applying it until you can no longer apply it. And then so the limit as x approaches infinity of the derivative of top and bottom. That would be infinity over infinity. Apply again. Limit as x approaches infinity of top and bottom. Derivative of top and divided by derivative of bottom. And finally, you no longer have an indeterminate form, and you can see that the output is infinity. All right, so 2 cases. All right, so consider this. Again, you have, for this particular limit problem, it's indeterminate. It's of the form infinity over infinity. So take the derivative of top and bottom. And when you do that, it transitions to a 0 over 0 type limit problem. Okay, but I believe you might be able to simplify this algebraically. Let's check the next slide. So here we go. Yeah, so when you simplify it algebraically, when you simplify this rational function algebraically, it becomes 3 over the cubic root of x. And then so when x grows very, very large, it overpowers the numerator, and so the output becomes 0 in the limit. All right. All right, in this case, limit as x approaches 0 of tan x minus x over x cubed. That's a 0 over 0 type. So applying L'Hopital's rule, the derivative of the numerator is secant squared x minus 1. The derivative of the denominator is 3x squared. So again, that's an indeterminate type, so you'll have to apply L'Hopital's rule again. And so it's 2 secant squared x tan x over 6x. Okay, so in this case now, even though you can apply L'Hopital's rule here, there's a more efficient way of evaluating this limit. And it turns out that the limit as x approaches 0 of tan x over x is equal to 1. Okay, so you can basically take that away and then use direct substitution. The limit as x approaches 0 of secant squared x, of course, is 1. So by inspection, you can ascertain that that limit's going to be a third, as opposed to having to apply L'Hopital's rule again and having to take the derivative of the numerator, which will be somewhat complex. All right, so look for simple solutions before you run off and take derivatives of complicated functions. Yeah, so there it is, 1/3. Okay. Okay, so yeah, so forth, so forth. All right, so how about this? Okay, now this is a trick question. L'Hopital's rule is not applicable to this function because if you use direct substitution, approaching pi from the left is in the domain of this function, because what is the cosine of pi? The cosine of pi is -1. Okay, and if you use direct substitution, you can use direct substitution on this. This would just be 0 over 2, which is equal to 0. And so here the author cautions you against having to invoke L'Hopital's rule. If you were to use L'Hopital's rule, you get minus infinity as the result, and of course that's not possible. It doesn't even make sense. So bear in mind that pi is in the domain of the function, so be careful when you apply L'Hopital's rule. Make sure that the rational function is in indeterminate form. Okay, next slide. Next slide. Okay. All right. So the output is 0. All right. Okay, so now we have also the idea of indeterminate products. This slide's a little bit jumbled, but an indeterminate product will be like this. And typically, what an indeterminate product is, it'll look something like this. It'll be like 0 times infinity or infinity times infinity. So indeterminate forms, if you have an indeterminate form would be something like 0 times infinity. And what you have to do is, for a product, you have to cast it as a quotient, a rational function. And the way you can achieve that is to take your g, take the reciprocal of g, and then divide f by its reciprocal so that you have a quotient. Or you can do it vice versa. You can divide g by the reciprocal of f. And so when you do that, it converts the given limit into an indeterminate form 0 over 0 or infinity over infinity. So that you can use L'Hopital's rule. Remember, L'Hopital's rule typically applies to rational functions. And so you can convert the product into a rational function. Okay, so for instance, consider this. The limit as x approaches 0 from the left of x ln x. Okay, so it's indeterminate because this essentially is a 0 times infinity or negative infinity product, which is indeterminate. 0 times infinity is an indeterminate product. Got to use L'Hopital's rule. So notice what they did. They took the original function right here, and then they took this x right there, and then they divided natural log by the reciprocal of x. So this function right here is equivalent, and it's an irrational function. And now you can invoke L'Hopital's rule by taking the derivative of upstairs and downstairs. So that's 1 over x divided by negative 1 over x squared. And then when you simplify this algebraically, it becomes negative x. So the limit as x approaches 0 from the right of negative x, of course, is 0. So the resolution of an indeterminate product. Okay. All right. Or you could do it the other way. You can convert it to a 0 over 0 type. Doesn't matter. Yeah, so you try to do it that leads to the simpler limit. Okay, now other indeterminate form types, infinity times infinity, okay, or I'm sorry, infinity minus infinity, okay, not times infinity. I think infinity times infinity is a determinant. So, you know, infinity times infinity is determinate. It's not indeterminate, but infinity minus infinity is considered indeterminate. Okay, so again, you have this. You have to convert the difference into a rational function. So consider this limit. Obviously, if you plug in pi halves, you'll have an infinity minus infinity. So in this case, for this particular limit, what you'll have to do is you'll have to subtract the two functions using the definitions of the two functions. And so that's done here. So secant x minus tan x. Okay, replace secant x with 1 over cosine x, replace tan x with sine x over cosine x. Do the subtraction. You can see now it's a 0 over 0 type. Take the derivative of upstairs and downstairs. Okay, when you do so, you can then use direct substitution for this limit, the last limit shown here, and that of course will be 0. So this limit then, right here, is equal to 0. Okay, all right. So differences, infinity minus infinity. Okay. And then, of course, we have what are called indeterminate powers. So maybe the case that you're asked to find the limit as x approaches of a function raised to the power of another function. And so it could be that, okay, so you have 3 different cases in general. Could be that f resolves to 0 and g resolves to 0. So anytime after direct substitution you get it resolves to 0 over 0 case, then, or 0 to the 0, that is, this would be indeterminate. Infinity to the 0 is indeterminate, and 1 to the infinity is indeterminate. Okay, so these are all indeterminate types. Or 1 to the minus infinity is indeterminate as well. Okay, so 3 indeterminate power format. So now we need to discuss how we compute the. Okay, so the way you evaluate those types of indeterminate forms is you take the natural log of both sides. So understand that when you take the natural log of both sides of this equation, g of x becomes the coefficient of the natural log of f of x, okay? And then the natural log of y as such. And then, of course, then you just take the reciprocal of g of x. You take the natural log of f of x and divide it by the reciprocal of g of x, evaluate that limit, and then take the exponential of both sides. We'll see that in just a second. All right, so far, pretty straightforward stuff here. Not like chapter 2. Okay, so we have some examples, probably do. Let's do some examples. Oh, I lost my slide, okay. Slide 51. Slide 52. All right, yeah, so here's a good example. Calculate the limit as x approaches 0 from the right of 1 plus sine 4x to the cotangent x. Okay, so using direct substitution, the indeterminate form is of the form 1 to the infinity. Okay, so now you have to use L'Hopital's rule. All right, so that's a 1 to infinity type. So let's go to slide 53. So in slide 53, let y equal to the function, and then take the natural log of both sides. So the natural log of y is equal to the natural log of this, and then the cotangent function right here, the exponent becomes the coefficient. Now, what we'll do next, of course, is we'll replace the cotangent function with its reciprocal. We'll divide by the reciprocal of the cotangent function, which of course is tangent x, right? So we can do that. So that would put it in a rational form compatible with L'Hopital's rule. So that's probably the next slide, 54, right? Slide 54. Okay, so yeah, so here you go. So the limit as x approaches 0 from the right of natural log of y, then is equal to the limit as x approaches 0 from the right of this function. So now we can use L'Hopital's rule, taking the derivative of the numerator. Now remember, when you take the derivative of a natural log of a function, its derivative is the derivative of the function divided by the function. Okay? So remember that little rubric for taking the derivative of the natural log of a function. So the derivative of the function is 4 cosine 4x by the chain rule, divided by the function itself, and then we take the derivative of the tan x, which is secant squared 4. Okay, so now we know then that 0 is in the domain of this function, so that goes to 1. This goes to 0, and this goes to 1, so you have 4 over 1. Yeah, so, okay, so that, now, so we have the limit as x approaches 0 from the right of the natural log of y is equal to 4. So we're not quite done. We need to replace the natural log of y with y. So that'll involve some additional computations. All right, so that'll be the next slide, slide 55. So, all right, so we have, okay, that's not very useful there. I don't like that slide. So let's go back to slide 55, or slide 54 rather. Okay, so let me explain to you theoretically what's going on here. All right, so we have the limit, well, let me do it on slide 54. Well, okay. We have ultimately this limit that we need to settle. The limit as x approaches 0 from the right of the natural log of y is equal to 4. So how do we figure out what the solution is to the original problem? All right, so let me copy this. Let me try to copy it. It's not letting me copy. Okay. Well, anyhow, I'll do it on the next page, 55. I'll fill in the missing details for slide 55. If it'll let me advance. Okay, so here it is. This is slide 55. Is that it? That's not slide 55. Slide 55. I guess that is slide 55. All right. So what we were left with is we had the limit as x approaches 0 plus of the natural log of y is equal to 4. Now, we need to resolve, we need this though, okay? So to get rid of the natural log, what we'll do is we'll let the left-hand side become the exponent in the exponential function, like so. Okay, so we'll take the exponential of both sides, and then that would equal to e to the 4. Now, so by the limit laws, okay, So we're left with having to reconcile e to the limit as x approaches 0 plus of the natural log of y is equal to e to the 4. Now, by the limit laws, since the exponential function, e to whatever, is a continuous function, we can take the limit operator outside of the exponent. Okay, this limit operator right there, that can be taken outside. And so, in doing so, by the limit laws, we can only do this because the exponential function is continuous. It has limits everywhere. Okay. And so now we recognize that this is just the inverse function theorem in play. So this implies, e to the natural log of anything is anything, okay? So the statement then simplifies to the limit as x approaches 0 from the right of y, therefore is equal to e to the 4. So that's how you would conclude the argument. Okay, so let's see, next slide. Where was that, slide 56 now? All right, so we want to calculate the limit as x approaches 0 from the right of x to the x. Well, okay, that kind of looks like the exponential function, but if you use direct substitution, clearly that's a 0 to the 0 type, right? That's 0 to 0, so that's an indeterminate form. So that means we're going to have to take the natural log of both sides. All right, so in doing so, okay, so x to the x is equal to e to the ln x to the x, okay? Right? Okay, so we readily see that. Well, it's not very intuitive the way they did it. So let me fill in some detail, some missing steps here using the exponential properties. Okay, so x to the x is equal to e to the natural log of x to the x, okay, which is equal to e to the x ln x, okay? And so if we want to take the limit as x approaches 0 from the right of e to the x ln x, then we can take the limit operator and just move it into the exponent by the limit laws. Okay, so you should be getting used to moving the limit operator in and out of the exponent. Okay, x ln x. But turns out that we've already found this limit. Okay, that was one of the previous examples that we did. And what was it? It was 0, right? Okay. So if you go back in this video and look at that example, we calculated this limit. And so, all right, so that's 1. Okay. All right, so that's L'Hopital's rule in a nutshell.